Okay, so looking at forces as vectors. So a vector is a quantity which has a size and direction. We can use I and J notation to represent a force. We haven't done much on I and J notation in pure maths yet. It is coming up. It is the last chapter of pure maths, but we did talk about it in chapter 1 of mechanics. But just to have a quick recap on vectors, just to make sure we're all happy with it. So we've got displacement, velocity, acceleration. They are all vectors, and what a vector includes is a magnitude and a direction. Instead of displacement, a scalar for that would be distance, and that is just a magnitude. So if I walk from my house to the shops and it's 2 miles, and then I walk back, my distance would be 4 miles, but my displacement would be nothing because I've gone there, which would be 2 miles, and I've come back, which is minus 2 miles. So that's what we mean by having a direction. So if we've got velocity and it is 3 meters per second to the right, the speed would just be 3 meters per second. Acceleration doesn't have a different word for the scalar, but you tend to see in the question magnitude of acceleration. So we saw acceleration being 9.8 when we were doing vertical motion, and that would be acting downwards. So we would use it, if we were taking upwards to be positive, we would use it to be minus 9.8, and that's where vectors are really useful because the sign can be included as part of almost what we've just been doing in the last section, where we were adding and subtracting things depending on which direction they were pointing. So IJ notation, you will have seen at GCSE when you've been doing translations, you will have written vectors in column notation. You might have even done IJ notation at GCSE. So if I wanted to go 3 across to the right and 4 down, rather than writing all those words, that's way too many words to be writing, we would say 3 minus 4. But not writing it as a coordinate horizontally, we write it as a vector vertically. In terms of IJ notation, that's 3I minus 4J, so it's just telling us we're going to go 3 across and then we're going to go 4 downwards. So that would be the vector that we're working with there. So I'm going across 3 and then I'm going down to minus 4. I is just a unit vector. So I has length 1 and it goes to the right. J is also a unit vector, so it's got length 1 and it goes upwards. So it's just using those set directions of 1 to the right or 1 upwards to be able to describe anywhere on a coordinate plane. So those two are unit vectors. Just like any unit, so if I wanted 5 centimetres, I know that that's 1 centimetre 5 times. So if I want 3I, I know that the unit I is 1 across, so I want to go 3 across. So it is being used in the same way. One way that we've seen this before, so a ball is projected upwards from a point 3 metres above the ground with speed of 2 metres per second. So we use signs to explain directions. The direction of a force is important, therefore force is a vector, so it works in exactly the same way as this. So looking at 2.2.1, so we've got two forces, A and B, acting on a particle P. Draw a diagram to represent these two forces. So if we focus on force A, so that's 2I plus 3J, we want to go 2 across and 3 up. So it would look like that, and you tend to put your arrow in the middle of your line when you're dealing with vectors. So that's vector A. If we want to draw vector B, then we need to go 4 across and 1 down. So it would look like that. So we've got those two vectors, and that's acting on our particle P, which would be at the origin on our diagram. So part B, find the magnitude of the resultant force acting on P and the direction in which it is acting. So the magnitude, size, resultant force, so you'll see that word coming up quite a lot. So resultant is the sum of the forces acting on the particle P, and we'll worry about the direction in a second. So when we're looking for the magnitude, this is a lot easier than it is with some of the other forces, because the i's and the j's are already worked it out for us. So all we need to do to find the resultant force, so let's look for the vector first of all, is to take each force and add them together. Now, because the signs are already included, so that minus j is already included for moving downwards, I just need to take the vectors as they are and add them, which makes it a little bit easier. So then we've got 2i plus 4i is 6i, so we're collecting like terms, so we'll collect the i's together, and then I've got 3j minus j. So my resultant force is that. I have been asked for the magnitude, so that means the size. So if I'm looking for the magnitude of a vector, this is exactly the same as what we looked at before. If we consider this vector, it's going 6 across and it's going 2 up. And I want to know what the magnitude of that force is. So that's that length there. So the magnitude, we use vertical lines around the letter that we're finding the magnitude for, although don't worry about that too much today. And then by Pythagoras' theorem, it would be r squared, so that's r squared is equal to 6 squared plus 2 squared, and because because the force is always going to be the hypotenuse, I can just skip that step and put it so that I've got the square root ready. So we've got 36 add 4, so that's root 40, which works out at 6.32 newtons, and that's to 3 sig figs. So that is the magnitude. We've also been asked for the direction. So the direction, as I mentioned earlier, is the angle. So when we're looking for that bit, I'm going to look for this angle here. So to work out the direction, I want tan. It's always going to be tan, because I've always got the adjacent and the opposite because of the IJ notation, so it's always going to be this way, and therefore we can work out that theta is equal to 18.4 degrees. So for part C, we are told a third force, xi plus yj, which puts the particle in equilibrium. Find the values of x and y. The resultant force is 0 when we're in equilibrium. So we've got the forces A plus B, which we've already calculated A plus B, so we know that we've got 6i plus 2j, and then I need to add my third force on, and that has to equal the 0 vector. The 0 vector is just 0i plus 0j. Just like before, if we collect our like terms, so collect the i's together, so I've got 6 plus x for the i's, and then I've got 2 plus y for the j's. And what we know is that needs to equal the 0 vector, so the I component and the j component have to be 0. So that tells me that x is equal to minus 6 and y is equal to minus 2. So C is equal to minus 6i minus 2j.